Testing 1, 2, 3. Testing 1, 2, 3. Okay, thank you, Jackson. Okay, good morning, everyone. Afternoon, noon. Nice to see live people in color. Yeah. I'm not Conrad, I'm Lyle, the other half, and we'll be changing off other pieces. And the schedule will look sort of the usual piece, except that Zoom is in the way. Here we go. Quick admin. Quick overview of how deep learning fits into machine learning. Again, a bit of optimization for the coming week, and then ending with some fun, sort of more contemporary arguments on things like double descent, which we'll define and talk about why optimization in machine learning is interesting. You should all have noted, first of all, that there is no final exam. We've decided it's not really necessary. This course is more about doing things. People can focus more on the final projects. We're writing up details on the final projects. Okay, gives the double thumbs up. Coming soon, soon, soon. Finally, we have shifted, as I hope you noticed, to Ed platform for questions. Please put questions there. We will try to answer them all there. I tried to be on there too. And everyone, any bureaucratic questions? Apologies, there's been a little trouble still with some of the worksheets being submitted. We're still debugging new systems. Questions? We're good? We're good, okay. Good, I want to talk, those who've seen 520 with me know that I think that all of machine learning is only three things. Representation, what equations you use to describe the world, and loss function, what do you try to minimize, and optimization, what is the process you use to minimize the loss function. And all of those are deep learning, so we'll do them today. One of the things that people had a little questions on the homework was what is inductive bias? Now, first of all, bias is a terrible word in English. In machine learning, it means three things. One is the bias term, which is the constant. When you fit a model, it's W times X plus a constant called the bias term from electrical engineering, the current that keeps flowing. It also means bias against people. Do you say, okay, we're going to charge more to you because we don't like you or because we like to exploit you? That's a form of bias. But inductive bias is a different sort of bias, which is what do you expect the form of the data to have? And it's sort of a folk theorem in machine learning that there is some equation that's right for describing anything, and there's some equations that are arbitrarily bad for describing anything. So anytime you design a neural network or write any equations, you're making some assumptions about the structure of the world, right? You have some sort of inductive bias. Is the world linear? Is the world nonlinear? Are there interactions? Is the world smooth? As you change X, does Y change smoothly? Is the world hopelessly complicated? Parity, right? The generalization of XOR problem, almost unlearnable, and can be exponentially hard. What bias does a convolutional neural net have? What does it assume about the world? Yeah. Translational invariance, first of all. What else does it assume about the world? You got little filters, right? Little regions. It assumes that you can find useful signal by looking in one local region of the world that there's high correlation among pixels that are close and lower correlation among pixels that are farther apart. It assumes that a good feature detector, which is what a CNN is learning, looks in some local region. It's not the case, assumed by a CNN, that a feature here and a pixels over there go together to make a good feature. It's a little window that scrapes across the world. This is a radically strong assumption that you can understand the world by looking through a little window and moving it across and scanning and scanning and scanning. Does that make sense? Does that work well? It's genius. Where do they get that idea? Your visual cortex, which confusingly is back here. That's our local receptive fields. That's the way that humans and rats and most animals see, is they have local receptive fields, little filters. Turns out that the world is structured that things that are close tend to be similar and that there's edges and colors and textures. Right, so those are obvious inductive biases. LSTMs, which we haven't covered yet, of course, but you've mostly seen them in 519 or 520. What assumption do they make about the world? Sorry? That the history tells about the future, but what form does the history tell you about the future? Is every place in history equally likely to be important? The recent history, you can sum up all the recent history in a local state vector. And in fact, that's different from methods we'll cover later, like transformers, that take all of recent history and say everything's equally important, no matter how far back you go. Do you, well, I can tell you we're not out of memory. Do you think that history is forgotten exponentially quickly? Or do you think that anything in the last 400 words is equally important? Those are inductive biases. Some of them are more accurate, and some of them are faster to compute because you can do the whole thing in one batch as a vector operation rather than cycling over history. Other biases built into neural nets these days? I used to be a chemical engineer, and it turns out there are certain things that are conserved. Mass and energy, for example. I don't do nuclear reactions. Mass and energy are conserved. You can build that sort of a constraint into your neural network, right? Here's all of the energy sources coming in. They've got a sum so that whatever goes in goes out or accumulates. That's a constraint you can put on the world. Do animals have inductive biases? My colleague Marty Seligman, guy at Penn, talks about the sauce béarnaise phenomenon. He ate this fancy French sauce, goes out to the opera. He sort of likes to go to his opera, goes home and gets sick. A month later, he goes to the restaurant. Does he feel sick when he hears the opera music in the background, or does he feel sick when he tastes the sauce béarnaise? The taste. Humans, like rats, learn. There's a lot of experiments on rats. Marty's not a rat. There's lots of experiments that show that you tend to associate stomach aches with flavors and smells, not with sounds. That's an inductive bias. Make sense? What else might you assume? What's important for predicting this? Does color matter? Can we be black and white? Does texture matter? What scales matter? How fine grained do we have to go? Right? Lots of things matter. And it's almost impossible to learn if you don't actually build some of these things in. We often assume in building extra data, there's a left-right symmetry. If you swap an image left to right, the label doesn't change in general. That's an assumption that we often make in deep learning. You could swap an image top to bottom. We don't do that as much for generating data. Why not? I look at all of you. And almost all of you, no, every one of you has a head on top and a body underneath. There are none of you that have heads on the bottom and bodies on the top. Where does the lighting come from usually? Up top. If you're trying to do shape recognition, if you assume lighting comes from the top, you can do a better job of finding things. Smoothness, what level of resolution? Again, I said that before, but there are huge assumptions in neural nets. We say we can fit any function, right? Universal approximator. Yeah, but the more jaggedy and jumpity it is, the more you need. To be able to fit it reasonably, you need some sort of smoothness, right? Usually we have some sort of Lipschitz continuity, that things are fully smooth. There's no big jumps in the world. So all of the modeling, you'll be building in some sort of inductive biases. And the more and more advanced you get, the fancier the inductive bias. So I assume that the world has one face in it, lots of objects. Do I assume that I can decouple in language content from style? Can I pull apart what I'm saying? I went to class today from how I'm saying it. Briefly, fancily, angrily. Make sense? So people build these structures into the neural nets. Questions, comments? This, I think, makes sense, but so much of the design is picking the right inductive bias. Cool. ReLUs, we talked about this last time. Why does everybody use ReLUs now? Nobody uses these nice hyperbolic tangents or other nice differentiable smooth functions. Closer to linear regression, but why do I care? Yep. Mostly because it's computationally cheap. That's in fact the key reason that they really won, because you're limited always by compute power. And you can say it's great if you're OpenAI or Google or Baidu, don't you have a lot of computers? And the answer is yeah, and it's still really expensive to train big models. They also are nicely differentiable and seem to work well. Better to have deep networks or shallow networks? There's a sort of inductive bias. Which is better? Well, someone's taking a 520 with me. It depends, right? If you've got enough data and the world is highly nonlinear, say image recognition, the deep networks win. For a lot of data sets, I work a lot also in the medical world, you've got not a lot of data. You just don't have enough degrees of freedom to fit a fancy deep network. And the shallow ones, like a simple logistic regression, work really well. If you get more parameters, you tend to overfit. We'll end today talking about that. But you need to think about these things. Loss functions. What's the right loss function? Of course, it depends.
All right, we're good.
We've seen several of these.
And that place looks gas, bro.
Mean squared error.
Money situation. That's the big.
Or L2 squared. Mean absolute error L1. I don't think we've seen cosine similarity, which is that you take your output vector from your network and you take the dot product of that with the true output vector. That should be the k-dimensional output. Dot product them, normalize them so it's an angle. Divide each by their norm. When might that be useful? That's one we haven't really talked about. We talked about squared error, absolute error, maybe for image. We talked about cross entropy, where you have a one-hot encoding of the answer. Why a cosine? I mean, sometimes your output is a vector, and you like to be close to that vector in some sense. But why not use L2? There's distance. What's different about sort of a cosine from the angle between two vectors versus the sum of squared error? Yeah. If the vectors are high dimensional, the distance can be huge regardless. Sort of all vectors are sort of orthogonal. What about the vector length? Sometimes you care about how something is pointing, but not how long it is, right? If I have one vector here and another vector that's much shorter, the L2 distance is big. This one's much bigger than that one. Sorry, the people who are remote can't see me. Vector here, little vector here, point in the same direction, sum of squared is distance, but they're pointing in the same way. The angle's 0. They're well matched. And so you often care about how close things are in the same direction, but not directly how long they are. I do a lot of stuff with words, and some people have more words, and some people have fewer words. L2 or L1 distance. I don't really care about who's producing more words or fewer words on Twitter or Facebook or text messages. I care that using the same words, right? Are the words close in some sort of a sense? And that might well be a cosine distance between the word counts in the one person and the word counts for the other person, right? Lots of words, lots of counts. We okay? Ah, thank you. Good, good. Sorry? Ah, questions in chat. Cool. Let's see if we can find questions. So we have invariances. Would the preferential selection of certain loss functions be inductive bias? Yeah, that's sort of an interesting question. Normally people think of inductive bias in the representation, but in some sense, the loss function is also a bias of a sense. It's what do I care about? I guess it's less a inductive bias in the sense of what's the world look like, right? Usually inductive bias is about representation, but it could be about search. Search first for things that are simpler and then for things that are more complicated, which we often do. How do we search for simpler models before more complicated ones in deep learning? Is that bias in there somewhere? I'm claiming in deep learning, there's a bias that we prefer to look first for simple models, smooth models, and only later do we try and look for more complicated, more wiggly models. I'm asking, how do we build that bias in? Regularization is a form of bias, assumption of smoothness, but how do we look first for smooth and then for bumpy? How do we initialize deep learning? Big weights, little weights. Little weights. What do little weights assume about the world? Smooth, right? If the weights were all 0, the output's a constant. We start with little weights, which gives a smooth function. Then as we learn, we get less and less smooth, right? So there's an assumption that we're starting looking at smooth things. And we'll see that optimization has some of that effect as well. Cool. I'm not going to talk about cross entropy again. I'm assuming people have seen it. But this is a very popular piece. If you have, I said I wouldn't talk about it. I won't read this whole slide. But often you have something, a one-hot encoding, some vector, which is one of the k possible things is on, the rest are 0. And what we often do is say, for each of the things we're predicting, we want minus the 1 for the correct answer times the log of the prediction, which says that we want something that feels like an entropy, right? The log of the probability of the correct answer. Works really well. Cool. There are lots of other cost functions out there. Conrad talked about some of these last week, but it's so important. I have to say them again. Often there's a different cost of a false positive versus a false negative. Build that in. Often you have some sort of constraints in the world. We'll see some examples of those. Regularization. I saw a cool talk last year where they regularize the neural net to try and make all the probabilities of the outputs closer to 0.5, right? So that's the way of smoothing the output rather than shrinking the weights. That was bad. Shrink the outputs. Hello, okay. Toward 0.5. Make it, and they did better out of sample performance. We'll talk about fairness in a second. So often you have some sort of piece. Cool example, and we'll talk later about using GANs to do these. But for the moment, you would like to do something that takes one sort of image, say a picture, and transform it into something that's artistic, has some different style. I try and do the same thing with language. Take in some language, some sentence, transform it to a nicer, friendlier statement that means the same thing, right? So style transfer. And you can see that in some sense, this image over here is close to this image over there. And in some sense, it's not close. Make sense? It's a picture of the same thing, but it's generated. Questions? You following the problem before we do the solution? Cool. So what can we do? We can say that we'd like to have, in some sense, the representation of the input picture be close to the representation we're learning. And one measure of close is to say that what happens is if you run these things through a neural net, each layer of the neural net transforms the original image into some deeper representation. Whatever a deeper representation means, but you hope it captures what's there rather than just the superficial picture, the color maybe. And one way to look at that is to pick some layer. And this is they're picking here layer 1, looks like an eye, but that's a 1. You could pick the output of the first layer, which is an encoding of the image. You could pick any layer, right? You could pick the last one, the almost last one, whatever, right? Pick some layer, depending upon how far in you want to go, how abstract it should be, right? The original layers are feature detectors. The later ones tend to be more semantic, more meaning of what's there. And you'd say, what I want to do is to have in my original image, the output of the first layer be close to the output of the first layer in the generated image. Does that make sense? As I morph this image, I want to keep it close in some sense. And some sense is close in an embedding space. Right? If you believe the embedding captures what the image is a picture of, then if it's close, it's still a picture of the same thing. Make sense? Now you can run an optimization that says, okay, let's try and do something where we try and keep, and I'm not going to go into the details here, but keep the synthesized and the reference image be close. And you can take things that say, okay, do various amounts of mangling. And depending on how much you change the image, it starts from something closer to the original buildings. And as you change the parameters on the -1, 2, 3, 4, becomes more and more disoriented. So you can force different forms of what do I preserve? Do I try and preserve the colors or let them shift? Try and preserve what the objects are. Try and preserve how the objects are placed close to each other. Different layers have different information, and you can hold those more constant. Right? It's a soft constraint, but you can penalize strongly how much you change them or don't change them as you push it away. Cool. So you can then take whatever you want and transform your favorite picture. That looks like a Van Gogh to me, Starry Night, to some other style by pushing it away in some directions and holding it close in others. Questions? I don't find the art super useful, but I'm a language guy. To do this in language is super useful. Can you take some language and shift it to make it friendlier, to make it more agreeable, to make it nicer, while keeping other things constant, like what it's talking about? We're building therapeutic agents that try and talk with people. You want them to be friendly, yes. Yeah, how do you select which layer to put the constraint on? The answer is try it, but I think the answer is also, what are you trying to preserve? So as you go deeper and deeper in the network, in general, what you go, the initial layers are local feature detectors. And as you go deeper, they become more and more, the fancy word is semantic, right? This one detects edges, farther in says trees, houses, people, bears. And so what do you want to preserve? I don't know, this is art. There's no right answer. But what things do you want to make similar to the previous model? And which things do you want to left shift? There's a whole industry in deep learning called probing, where you take the output of any given layer and then run it through a simple linear transform to see what you can predict with it. Can you predict what objects are there? Well, if it's toward the end, yes. If it's toward the beginning, no. You can't tell which object is there from the first layer. It needs more transformations. So clearly, as you go deeper, particularly for images, it's quite clear. For language, it's messier. But in general, even for language, the initial ones are more detecting single word meanings, and the deeper ones are more detecting relations between words. And so the answer is, what do you want? And now there's a whole bunch of people like you guys making their living, going around saying, okay, let's figure out which layer I care about, and maybe let's push it to be something we care about. And then going in later on to say, oh, can I alter the image? So if I can find where inside the neural net it's generating the background or the foreground or the objects or the faces, I can go in and tweak that part of the image, right? But you got to find that. I want to hold most of the image the same, but change only the background or change only the person in the front of it. Make sense? But that requires poking around inside the network to try and figure out probing to see what's represented where. And since the representation is somewhat distributed, hard to find it. So there's a whole other field of deep learning trying to disentangle, to pull apart the ones and force background and foreground to have separate neurons so you can actually do this sort of hold this part, change that part. So a bunch of people doing cool stuff trying to go in and explicitly change little pieces of images, leaving as much as possible the same. We'll do some versions of that. We'll do GANs, generalized the adversarial networks later, generative adversarial networks. Cool. Questions? Any questions in the chat? Let's see. Nope. Cool. Okay. Another set of criterion, and the homework this week will talk about some of these, comes in the idea of fairness. The standard setting mathematically for dealing with fairness, which I blocked out their names. My colleagues, your colleagues, Michael Kearns and Aaron Roth have looked at, and many other people, says that there are two sets of people, some general class of random people and some protected class. Maybe it's undergraduates or whatever subset you care about. And there are lots of ways you might want to impose fairness. One fairness says that for two different classes, if you have the same input feature, you should have the same output. That seems almost trivial, but there was a period in American history when the banks famously did what's called redlining. They would take a map of Philadelphia and draw a red line around certain regions and say, if you're in that region, we won't give you a bank loan. So even if you were high income or whatever inside that region, which happened to have lots of African Americans in that region, this is of course illegal now. But one simple form of fairness says, if you split the world in different pieces, right? Indian Americans, Chinese Americans, and you have the same symptoms, you should get the same treatment in the hospital. Seems a reasonable low bar. Make sense? But there are other ones you might want that are different loss functions. So you might want to have an equality of outcome, not an equality of same input, same output. So imagine that you have two sets of people, one set low income and one set high income. In general, the rich people are more likely to get into a school like that. It's a well-kept secret that elite Ivy universities want to be inclusive, but when you look at the undergraduates, most of their parents are really wealthy compared to other Americans or other people globally. So you could say that's unfair. And again, my goal is not to be moral about it. My goal is to define a well-defined mathematical criterion you might want. And a different criterion would say, take these class, wealthy parents, poor parents, we'd like to accept the same fraction of people from each of these two classes. That will mean different inputs. Note that's a different loss function, a different thing you're trying to optimize, right? I want the best students with my normal loss function, subject to the constraint that group wealthy and group poor have the same chance of being admitted. Make sense? Very hot right now. How do you decide how you should do that, right? Maybe that's a fairer allocation. Or not, all right? There's not a correct answer here, but you should be aware that often you're trying to take your original loss function, modify it in some fashion by putting on either hard or soft constraints. Questions? Good, cool. Whoa. Other things one could do, harder. Talk about toward the end of the course, we do reinforcement learning. Most machine learning as we see it, and most machine learning, take a data set, fit a model, test on a test set. But that's not really how people learn, and it's probably not going to solve really hard problems. In general, what does the world really look like? You get a whole sequence of problems. Right? Imagine working for a company and you're Amazon and you're trying to figure out how to make as much money as possible showing ads. Well, the world keeps changing. There are new products, there are new ad opportunities, there are new channels to advertise over, there's new markets, there's new languages. Well, they're not new languages, but you go into new markets with new languages, right? You start with 40 languages, now you're doing 60. You want to generalize. Humans are pretty good. Once you learn 2 or 3 languages, you get a lot faster at learning the 4th or 5th. And if they're really close, right? If you're learning French and Italian and Portuguese and Spanish, it gets pretty easy to learn the 4th one because you've learned the other ones before. But neural nets are mostly not currently doing a great job of that. You want to learn a new video game, it plays a video game from scratch. But the fact that it's learned already 10 different video games should make it really fast. You with me? So maybe we want a different sort of loss function. I'm not going to answer the question today, but it's something to think about. What's a loss function as I learn a language or a video game helps me to be better at learning future video games or future languages? And it's funny. Got a friend who's a rabid video game player. He doesn't try and win the games. He just plays, he sees what's going on. It's sort of like, I used to think when you put rats in maze, they would run through the maze and try and find the cheese. I talked to the rat guys here. You put a rat in a maze, what do? Sort of like putting a cat or a dog in a room. They wander around, they sniff things, they check it out. You know, later on, if they're hungry, they learn where the cheese is, they run to it. But rats spend a lot of time, like anyone else, just sort of checking out the room, being curious. What's there? What's over here? Anything interesting? Yeah, okay. So Our neural nets currently aren't really good at doing curiosity, at learning things that might be useful later. The tiniest piece, what do we call curiosity in reinforcement learning? Exploration, right? There's an exploration-exploitation trade-off. And humans and other animals spend a lot of time doing exploration and then a small amount doing exploitation. Our neural nets mostly aren't very good at that. So I think it's an interesting question to think about what's the right loss function that lets you do a better job of exploring the world. But I'm going to wait till reinforcement learning. Cool. Okay. We now come to phase 2 of our 3-part talk today. Phase 2 is optimization. We're going to talk about the stuff that you'll see in the worksheets. I've already spent the first however many minutes, half hour saying optimize the right thing, pick the right inductive bias for the equation, pick the right loss function. Optimization is mostly about learning quickly, but it turns out that your optimization has a big effect on what solution you come to. And so as we worry about deep learning optimization, which will be versions of stochastic gradient descent, remember it's always how fast does it get there and where does it get. There's an awful lot of effectively regularization through optimization. Cool. Not just a minimum, a good minimum. If you look at various curves when you run your data, accuracy versus epochs, what's going on that far left one? First of all, is this good or bad? Accuracy is going down. How could it possibly do that? Can things get worse if you're doing gradient descent? Sure. How? Sorry? The learning rate is too high. You might jump all the way past the minimum up the other side and bounce higher and higher. Right? So we'll see lots of problems like these and try and some idea of how to fix them. There'll be a bunch of stuff in the worksheets. I'm not going to cover all of them. Some are sort of obvious. I'll talk today about the intuition behind these things. The worksheets include things like natural gradients, which are sort of cool and too expensive to use mostly, but give nice intuition. I want to talk about optimization landscapes. So we're going to look at clean pictures today, sort of two-dimensional representations, as if you only had 2 weights in your neural net. Of course, you got 2 billion instead, but I can't draw that very well. So we'll sort of try and picture a two-dimensional surface and realize that the real world is really ugly. And you can imagine starting at some point, and depending upon what optimization method you take, these little balls are rolling down the hill, right, to lower errors. And they may get into the local optimum on the right or the global optimum on the left. They may go slower, they may go faster. Everybody clear on the basic picture? Right, two-dimensional. Remember again, the high dimensions, life is really weird, but most of the intuitions carry over pretty well. And I've gotten links here to go play with some of these things afterwards. And particularly, I wanted to play with this one a little bit. It's sort of fun. So you can generate on this nice web page a bunch of different loss surfaces. This is a two-dimensional loss surface. And you can go play with it and you can pick some starting point. And it's now doing gradient descent. Oh, it's stuck. Why might it be stuck? Oh, it's going, it's going, it's going. How shall I readjust my gradient descent here? Let's see if I can make the thing go down faster. Boom, okay, speed it up. Oh, it's going fast. Get rid of the bottom. What happened when I got the high gradient descent rate? Let's do it again. Start another one. Start over here. Boom. Got to the bottom really quickly. It's too fast. Let's watch it once more. Boom. Uh-oh. Ah, okay, at the bottom. If you've got a high learning rate, gets there quickly, but what happens? Bounces out again, right? So we're going to want fairly shortly to have something that adjusts the learning rate to anneal or schedule the learning rate. We'll want to start with a high learning rate and then go slower, right? Because we want, as we get to the bottom, to stay there and not bounce out of it rather than zipping down and then, whoa, we go all over the place. Okay, so let's go back and change the learning rate. We can also adjust things like momentum, which will, oops, do another one. Uh-oh, now we're sort of stuck again. But sometimes momentum is good. Up, and now we got there, and now it's a nice learning rate, and we hung out there, right? So I've got a low enough learning rate, and somehow the momentum is, and we'll see in a second in the mathematical definition, momentum just means keep going in the same direction you were going. And sometimes it pulls you out of those local minima because you keep going, a low momentum, you go out of the local minima and then down again. So with a lower learning rate, you can still get out of those local minima. So almost all machine learning methods, deep learning methods use momentum now. Cool. You can play with these. They're so fun and they're so pretty and it's got nice things. You can have it rotate in 3D. You can generate different versions and it's all neat. But we're not going to do it right now. But there it is, lostlandscapeexplorer.com. Cool. So first concept, conditioning, matrix conditioning. If you look at most of the neural nets, what you see is the landscape has lots of really narrow, very deep chasms, Grand Canyons running through each other. It's not nice and smooth. It's incredibly jagged. And this makes optimization really hard. And in a simple version, if you look at it, if there's one version where the landscape is relatively flat, low curvature, flat, blue, low curvature, and one dimension where it's really steep, high curvature, oh, except there are 10 million, of which 5 million are really flat, and 5 million are sort of steep. Another 20 million are in between, right? So you get lots of dimensions, and they're really weird. Now, when you try to actually do a gradient descent, it doesn't work very well. Having slopes of different amounts is an ill-conditioned matrix, and the convergence ends up being pretty slow. If you look at what happens is, and here's something which has a one direction here which is flatter, and one direction which is steeper, right? These lines are lines of equal loss function. And what happens in the starting point is you go zig, 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 zig. You keep going down and down the valley. And you gradually move down. So you're wasting a lot of time going up and down the steep valley and only going a little bit in the flat direction. Because think about it. Where's the steep gradient? It's going down the canyon. Where's the low gradient? That's the direction you actually care about. Right? So you're spending all your time going up and down the sides of the canyon and no time going down following the center of the canyon, which is gradually going down, which ends up being incredibly expensive. Does this make sense geometrically? Lots of nodded heads. Cool. So what do? We will use momentum. When we update our weight, the new weight is the old weight plus a standard gradient descent. So that's just the loss function J of the weights with some learning rate eta, that's the normal gradient descent, plus a different constant times how much did I change the weight last time, right? So it just says adds on beta times how big a step I took last time. You can see it's momentum, keep going in the same direction. Very old idea, but works really nicely. If you do it, now, instead of zigging quite so much, you're averaging over the ups and downs of your valley. And we're still doing a little bit of zigzagging back and forth, but much less. So we end up much fewer steps to get to the bottom. And again, real deep learning models tend to have lots of these valleys in them. And so this tends to be a big win. Questions? You'll get to play with all these in the worksheets, but I think it's easier to understand them now. Okay, second concept. Rate scheduling, rate tuning, annealing. Simple version, update the weight by adding a learning rate times the gradient of the loss function with respect to the weights, the gradient step. You want to do something that says my learning rate will get smaller. Remember the first thing I showed you? Slow learning rate took forever. Fast learning rate zipped the bottom and bounced out again. So you want to anneal, to slow down the learning, make it smaller over time. There's a large theoretical literature, and unfortunately last year I had the TAs code up great examples that would reinforce the theory, and it doesn't seem the theory holds for a lot of real examples. So you can play with these again in the worksheets, but the concept exactly, should it be 1 over t, 1 over square root of t? There's strong theory arguing for both of them. I don't know, but some sort of annealing tends to be a really good idea. Start with big steps when you're far away. When you get closer and closer, make smaller and smaller steps. Again, worksheets will have this. Think this makes sense? Obvious? But good, cool. Moving forward, whoop. There are fancier versions of that one that says instead of annealing the overall learning rate, you should anneal or schedule every single one of the parameters. And so the standard way to do this is called attograd. This is sort of often the default learning rate. Update each weight as being the weight minus an overall learning rate times the gradient divided by the square root of the sum over all the previous epochs of the square of the gradient in that direction. So you have a million weights. For each weight, you keep track of the gradient in that weight direction for each of your last 10,000 steps, sum them up, and take the square root of the squares, right? So it's the L2 norm of them. So what does it mean? It means those weights that have had big gradients slow down their learning. The ones that have had small gradients tend to not slow down. This should sort of sound like the conditioning I showed you before, right? If you have one valley that's super steep, and even lots of gradients here and there, it's the sum of squared, right? The gradient on one side is this way, the gradient on that side is the other way, but it's the sum of the squares. You with me? So the steep valley direction tends to get rapidly downweighted, and the flat one that's sort of just creeping downward, not downweighted. Does this make sense geometrically? It's a clever idea. There's one problem with it. Anything wrong potentially with a annealing schedule? Yeah. They're not very computational. Would it be computationally expensive? Pretty easy, because you're just keeping a running total. So the total memory is the number of weights you have. You've doubled the number of weights, so that's not a bad thing. And you're just summing them and squaring them. You just keep a running total. So no, computation's really cheap. That doesn't cause any problem. Yeah. So if one of the weights becomes much bigger, you might dominate. I imagine you could get stuck. I mean, the version of it that happens is this is monotonic in the sense that the learning rate only goes down. It can never go up, right? The thing you're dividing by just gets bigger and bigger. And so in some sense, this thing may get stuck. It doesn't allow you to say, oh, oops, I'm now learning too slowly. Let me speed my learning up a bit. So if you look at these like demos, here's a version of the blue line, a standard gradient descent, the gray line, the attigrad, and the attigrad one is actually going in a much straighter line. That the gradient descent goes down the steep version first, to the sort of saddle point, and then down the other one. So the standard gradient descent goes first down the steep direction, and then turns around the corner and goes down again. Whereas the attigrad, the one I just showed you, says, oh, the steep direction is less important, right? Downweight it, and it tends to go much more directly in the direction it's moving. Cool. Fun. Okay. So there are a bunch of other versions, and there's two more that you'll see in the worksheets, which is that you can have sort of fancier readjustments to the learning rates. I think I'm not going to spend too much time to note on them, except that when you look at these, and oh, why does this computer keep, this is not my computer is great. That one over there keeps coming in and out. Yes, hello. We have a linking problem. I can see it fine. Okay, well, that's thinking about coming back. Let me just tell you what's going on. It's very annoying. So I will want this to come back. Okay, hopefully it comes back. The one can driving me crazy. Yeah, try and fiddle with it. So what a lot of these are trying to do is say, okay, what I want to do for each of the parameters is not just make the steepest one become less and less learning speed, but to readjust them in different ways. Oh, there we go. Magic. And so in this sort of cool visualization, you can see the RMS prop green ball going faster than the white one. But the weird thing is the shading, which shows that the gradient squared changes differently. So this normalization constant. Okay. I hate technology. What did we lose?
I just adjusted it to Zoom.
So as you go through the worksheets, try and think about the geometric interpretation, right? And you can go back, there are links in the slides for these nice, cool visualizations. But think about this as a landscape with some very, very steep directions and some very shallow directions. And what you're trying to do with your fancy gradient tuning methods is to adjust those so that you don't bounce up and down on the steep directions, but you keep moving as fast as possible on the relatively flat ones. And yeah. Bunch of them with other pieces. One last piece, which is really obvious. If the gradients are just really too big, what do you do sometimes? Simple hack. Clip them. Put a maximum. Just don't let the gradient get bigger than some number. Total hack. No theory, no nice geometry, but if all else fails, put an option that says, don't let the gradient get bigger than any certain number. Just max it out. Obviously an absolute value, right? Not bigger, not more negative. And there's code to do that in TensorFlow. Cool. So that's the speed, right? Readjusting how fast each of the directions goes. Then there's the question of what direction to move in. And sometimes you get weird things where your accuracy goes up and down and bounces around. And there are a bunch of pieces, and I'm not going to really cover them because the worksheets will do them. But we're going to use mini batches, of course, right? We'll do sets of roughly 50 or so observations for one time to take the gradient. Mostly computationally. If you had lots of memory, when I say memory, where does the memory need to sit if I'm doing deep learning? Where's the limiting memory for me, the expensive memory that I want fast? RAM? No, it's on chip. So remember that to do anything with any reasonable speed, you're using a GPU or TPU, which is the same thing, using a graphical processing unit. So think of RAM, the thing on your computer, on your laptop, whatever, as being the slow memory. That's like the disk, slow. You take the stuff off of your RAM memory and you send it to a GPU, which is going to do vector operations. You need to put the data onto the GPU. And you want fast memory on the GPU that's going to hold that data. It's going to then bam your vectors together to do your vector processing, compute the results, send it back out to the slow memory, which is your RAM. It's a weird way of thinking. This makes sense? So the limiting amount, the cost you're spending is you want to buy a GPU that's got a decent amount of RAM, but fast memory on the GPU. And why is that critical for batches? What's the limiting question of how big a batch I can do? Will it fit into the memory on the GPU? Make sense? Because if not, you're doing something like the old days, you would swap from disk. You would read the stuff off of disk, which took forever, and put it on your computer and then write it back to disk, which took forever. Now you're doing the same thing from your RAM to your GPU. But you really, 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 really want the batch to fit onto the GPU, in memory on the GPU. Make sense? And that's very expensive memory, it's fast. Cool. Good. So that's the size. I want to make sure my mini batch fits onto the GPU memory. Normalization. It's common to do normalizations across batches and normalizations across each of the layers within the neural net. Right? So imagine you're in gradients. Obviously, you got a gradient for every single layer of weights. Make sense? Why might you worry about doing different normalizations for different layers? And where do we see this before? Could have sworn Conrad talked about initializations. Pardon? The Xavier initialization. It was that, yeah. Anybody remember Xavier initialization? The idea behind it? Yeah. Want to keep the variance in each layer kind of the same, and particularly as you multiply through layers, things can get bigger or smaller. And if you're looking at gradients, the same way that you want to initialize using Xavier initialization to keep roughly a constant variance across layers, you might want to do something fancy that keeps roughly a constant gradient level across those. So you don't have some layers zipping wildly there and other layers going along more slowly. And again, I'm not going to walk through any details, and these things will probably be different in 2 years anyway. But the concept, I think, is important, which says that as you look at gradients, the gradients in different layers can be noticeably different. And that might mean some other way you should try and normalize them to make things move nicely. Ah, cool. What does it say? Yeah. Yes, so it is going back to the GPU. It is the case that it takes time to transfer stuff from RAM to GPU. And you certainly can't afford to be sort of swapping in stuff out. You want to put it on the GPU, do the vector multiply, put it out, and you are limited in transfer rates. Companies like Google are investing a huge amount of money in building fancy, fast devices to have fast interconnects, BIOS. Actually, how do you move the data really quickly within the same computer? How do you put it quickly onto the GPU and take it off again? Active area of hardware design, but not my thing. I just trust them. Okay, good. Final topic. Double descent and over parameterization. Let's make this go away. Yeah. So normalization versus normalizing weights in each layer or out of layers. Well, I think what we're thinking here is not normalizing the weights so much as adjusting the gradients. So think of the weights exist between two layers, right? Layer here, layer there, there are weights in the middle. As we pick all those gradients, we might do some sort of a normalization of the gradients there. And from the next layer to the next layer, a new set of weights, maybe a different adjustment of the gradient there. So I talked a lot today about each individual weight one by one, right? Downweight the learning rate for ones that have been changing a bunch. But you could also do some sort of adjustment at an overall batch level. Or you could say, I want these things on average to have this much of a change, this much of a weight. So I think just the big takeaway concept is that a layer is often a natural way to think in terms of how big should these weights be or how big should their gradients be. Cool. Okay. Oh, that's the wrong direction. If I were good, I could hit the right button. Boom. Okay. Good. So neural nets are often big. I picked ones from my area because I like language. The small network, so old-fashioned, but we'll talk about it later. GPT-3 has 175 billion parameters. My last slide had it wrong, not for you guys. I put million. Like, I thought it's not that small. Billion parameters. But the modern ones are bigger, right? So these are really big models. But when you look at them, the training sets are really tiny. What do I mean by tiny? For the GPT-3, it has roughly 500 million words of text. Why do I say tiny? I got 175 billion parameters, and I got 500 million words of text, right, for the self-supervised training. So I got 2 orders of magnitude more parameters than I have data. Holy crap. This should be a problem. Everybody see the problem? Let me remind people of the problem since we take things. Oh, I thought I put in a new slide for that. Okay. There it is. There's the slide I wanted. So machine learning 101 or 520 or 519. What do we have? Error versus model complexity. As the model gets more complex, the bias goes down. You fit the data better and better. The training error goes down. Bias, training error. Training error goes down the more complex the model. If you look at the variance, I'm not going to cover bias and variance. I'm hoping you've all seen it. The variance goes up, right? You refit on a different data set. It bounces around. It's different every time. And the bottom line is for machine learning, if you have too simple a model, you have underfit and you get crappy pings. There's some optimal complexity. And if you have too complicated model, you have overfit and your training error is gorgeous, but your testing error is high. Everybody remember this? This is the bias variance trade-off. Except now we've got a real problem if you were, say, a theoretician or an engineer, which is that what happens with deep learning? Where's this bias variance trade-off? Hello? And what you see with the model complexity, so this is just a measure of what the width of the neural net is. You make the model more and more complex. What happens to this case, the testing error? The testing error with no regularization goes down at first. That's great. Model's getting more complex. We're no longer underfitting. We get some optimum. Okay. The model starts to overfit. Error goes up. And then crap. Something unbelievable happens. The error on the test set starts going down again. This is the so-called double descent phenomenon, right? There's the obvious region you expect when you go from a really underfit model to the right size model. The accuracy on the test error gets better. Then it gets worse, as you'd expect by theory. And then it gets better again. There's a second descent. And where is GPT-3? Well, this is an image one, but it's way out past here, right? It's way out there in the massively over-parameterized. And again, I want to say that again. The region over here, under-parameterized, right? Not enough degrees of freedom, not enough weights. The region over here, over-parameterized, way more weights than you have data points. That's annoying. By the way, if you do early stopping, then you can actually control this and get this to be sort of flat across here. So this bottom line goes down, 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 and you get a sort of a flat line under there. So what do we have? We have what you might call a classic regime over here with a bias variance trade-off. And here, I've of course stolen these from the guys who wrote the paper with credit. If you look at the training error, it's in green here. Underfit, training and testing exactly the same. As you get to this point, the training error goes down, down, down. The training error goes down basically to 0, which is not surprising, right? You now have a lot more parameters than data points. You got this thing that's a universal approximator that can fit anything. You've done your nice tuning of your gradient descent, and well, I don't know what overfit means. If you believe overfit means that your training error is less than your testing error, you've overfit the crap out of this, right? On the other hand, say you were an engineer working for a little company like Google, where do you want to be in terms of model complexity? All the way at the most complex one, right? Your overfitting is giving you an optimal model. It's a little annoying. The theoreticians, their papers trying to do this with linear models and trying to work it out. But let me stop for a second. Everybody see the phenomenon? I wish I had a solution to it, but unfortunately I don't think I do. But so under-parameterized here, over-parameterized there. In under or over-parameterized regime, if you increase the complexity, it helps. In the middle, that bump, empirically adding more parameters may help, may hurt, who knows. Now the question, which I wish I knew the answer to, why do I want this over-parameterized model? And I think the answer seems to be that these models are all doing interpolation, right? So you're sitting in a very high dimensional space. Take the space of images or the space of words or sentences, very high dimensional spaces. And in some weird sense, all deep learning is just interpolation. It takes sentences or images it's seen and finds for a new one, it's somewhere in between a set of these. Right? It's almost like a very fancy k-nearest neighbor, but it learns the right metric in some nonlinear fashion, so it's very fancy. But it's some sense interpolating between the training data. And it seems that by having a massively over-parameterized model, you get really nice, smooth interpolations. That when you run your gradient descent, that's the second piece of the magic, gradient descent seems to magically converge more toward flat, big, smooth optima and less to deep, narrow, shallow, unstable optima. And again, there's sort of cool math suggesting that's the case. But the interpolation seems to be smoother and it just seems to work out more nicely. If you read the authors, in the over-parameterized regime, there are many models that fit the training set, and there are such good models. Moreover, the implicit bias of stochastic gradient descent leads to such good models, right? So stochastic gradient descent tends to take you to nice flat models that generalize well for reasons we don't yet understand. Bummer. So that is the state of the art. This is high-end people currently writing, right, within the last year or so. I don't know the answer, but it does seem empirically really the case that over-parameterizing works well, and that gradient descent in particular, if you were even more clever in infinite compute time and you run a genetic algorithm and you search over random stuff and you found a great solution, you'd be really unhappy. Because you'd overfit to the point you found some really deep chasm in the loss function, and it wouldn't generalize well, and it wouldn't be a nice smooth interpolation. So there is something about our gradient descent methods that leads us to come to methods that are nice, generalizing, smooth interpolations. And the last thought I'll leave you with here is that as you choose these different methods, like AttaGrad or RMSProp or the ones you look at, note that it's not just how fast they get there, but some of them converge to methods to solutions that seem to generalize better, that work better on the held out data, and other ones converge to ones that work less well, and that it is extremely common now to use these large over-parameterized models that should really overfit and that do have a training error way less than the testing error. But what you care about is the testing error. And so often you're saying, throw me more parameters, converge me nicely, and then just check the held out error and make sure that I'm converging to something nice. Cool. Questions? Yeah. Yeah, how does this work for smaller things like medical data? I think it's an open question. Almost all of this research is coming out of OpenAI/Microsoft or Google or places that are doing huge language and huge vision models. I think the problem is the phenomenon will be universal. And I think the medical world just hasn't figured out yet how to do this. I think there's a lot of openings for smaller data sets to ask the same sort of question, which is, how can we actually do something that overfits in the sense of training being way less than testing, but still does a better job? So I think the answer is, I haven't seen any good papers on medical data sets showing this double descent phenomenon, but I suspect it's there. It seems to be something that's fairly much innate to this deep learning sort of modeling. It'd be fun to try it. Have you done any experiment and you just tried the medical data? I have not run experiments on the medical data to see whether this works. It's tricky to find something that's complex enough you can beat logistic regression. But I think so the answer, I don't know. I'm predicting it will work. You'll have a similar phenomenon, but I don't know. It's really unclear because we don't quite understand this geometry of what interpolation looks like. And interpolation is sort of, at least for images, we've got a pretty good idea of what each of the layers do. And we sort of have a feeling of what interpolation means in the sense of being close in the neural net embedding space of images. For medical data, We haven't done as much probing. We haven't done as much thinking about what's going on. We don't really have a picture of the geometry of the space. It's obviously radically different if it's imaging, medical imaging versus EHR data. I don't know. This is, we're in the Wild West right now. Even the guys who did the classic stuff don't even know for the stuff they understand what's going on. How would they know about medical data? Great question. Be a fun final project. Cool. Yes. One more question in the chat. Okay. Let's see if I can find it. Boop. Humans have more neurons. Well, humans work really differently from, question is, does this also explain the fact that humans have more neurons and are more intelligent? And the answer is, we understand how the visual cortex works. We really don't understand how thought works and how people reason. And we know they're pretty different from artificial neural nets. And the answer is, I love speculating, but in this case, I'm not going to make any speculation about what this means for how human cognition works. You can try Conrad and see if he's a braver man than I am, but we really don't have a good feeling of how human brains are overparameterized and how they represent anything like concepts and relations between them. Bummer. Yes. Yep. So what's weird about a lot of learning, this was first noted in boosting, but now shows up in some of the deep learning, you can have stuff where the error goes down, training error goes down to 0, and you keep learning. So that as you're looking at the gradient steps, you're still adjusting stuff, even though your training error is very close to 0, there still can be further learning. So it's the same sort of weird phenomenon that says that as you look at this gradient surface and you find the gradients, as you get close to the 0 training error, the gradients are going to go to 0, right? You're getting sort of a flat sort of local place there where nothing reduces the error further, right? The error goes down to 0, but there's still a little bit of gradient. You're never numerically at a 0 piece there. And so maybe you're still learning a little bit, and maybe you're still reducing the testing error, even though the training error is visually not changing. So, but remember that it is still changing, right? The testing error is still going down a little bit because these are not 1, 0. You're doing like a cross entropy. So you're driving your probability of the correct thing from 0.9 to 0.92 to 0.93, right? So your error can be 0, but note that as your error is 0, your probability of the correct answer just has to be 0.51 to be right. It can still go to 0.8, 0.9, 0.99. So you're driving the parameters in some way that reduce the loss function. You with me? Even though the error in the training set doesn't change at all. And as you do that, you're still improving often your test accuracy. Now, sometimes you really are overfitting and it gets worse. So no guarantee, but it can still improve it. Yeah. No, the error is exactly 0. Will the loss be 0? They're two very, very different things, very important. One is the error in a 0-1 sense. Did you make the prediction correctly or wrong? Right? Was it a mask or was it a cat? That's a 0-1 loss. You got it right, you got it wrong. The training error I'm showing there is 0-1 loss. But the loss is not a 0-1 loss. The loss in these cases, that case is a cross entropy. It's a minus log probability. You with me? So the probability never hits 0 or 1. It's 0.9 to 0.99 to 0.9999, but the loss is never exactly 0 in the loss function you're optimizing. And that's, I think, a key point. There's a big distinction between the percentage correct loss and the loss function you're actually minimizing. And the key point is, even after you have 100% accuracy on prediction, you can still drive down your cross entropy loss, right? And sometimes, often, that still decreases the testing loss, right? And it's a little counterintuitive, but that's what people are finding. And again, it doesn't have to be the case. It could well be the case you will just overfit the crap out of it and your testing error will go up, but it's something to watch for. Cool, we're at time. Thank you so much. Have a good week. Enjoy playing with these. Have some fun playing with these. They're such fun things. See you all online on Ed.